Hi everyone, welcome back. Let's write some more Leetcode today. Today we are solving most profitable path in a tree. So this problem description is a bit long, so if you want to read it all, feel free to do so, but I'll try to summarize it in as short as possible. So basically, there are two characters in this problem. There's Elise and there's Bob. Elise will always start at node 0, and Bob will start at whichever node the Bob variable is. And they will both move to one adjacent node at a time. Bob will always move towards node 0, and Elise will move towards any leaf node of their choice. And at every leaf node, if it is untouched, then they receive the full reward or they pay the full price, depending on if the number is positive or negative. If they reach the node at the same time, then the price or the reward is split in half. And if the node has already been touched or if it has already been visited, then they don't have to pay any price or receive any reward. So therefore, the problem is that for Elise, we want to return the most income that she can receive by choosing the optimal leaf node. So for this example, as you can see, the output would be 6 because she would receive the most income by coming towards this way, because at 2, we would subtract 2. At 4, she only gets half since Bob moved here at the same time. So 2 minus 2 is 0. And at 3, she wouldn't need to subtract 4 because Bob has already been here. And at 4, she would gain 6. So that would be the optimal output rather than coming to this leaf node where she only gets 2 net income. So now that we have seen some examples, let's get to how we can solve this problem. So one way that we can solve this problem is we will set up a tree list where it has all the adjacent nodes to its node. And then we will also have a Bob distance list where at each node, it will list down the time it takes from Bob to get there. If Bob will never touch it, then we will set that to the length of amount. And initially, we will set every index to the length of amount except for the starting index of Bob. And then we will also have a time array to keep track of the time it takes to get to certain nodes. So if the time it takes is less than the Bob distance at that index, then we will get the full reward or pay the full price. If it is equal time, then we will get the half price or half reward. And if it is greater than, then we don't do anything. So what we will do is we will do a DFS search with Elise to all these nodes. And at each of these nodes, we will add the maximum path we can to the result. And then after having done a DFS search on every single pathway to every leaf node, then we will return the maximum income that we can, and that will go to result. So I think it will make more sense as I go over this example, and it will make even more sense when we get to the coding part. So let's go over this example first. So in this example, we will first set up this tree array. So as you can see, node 0 is adjacent to node 1. Node 1 is adjacent to 0, 2, and 3. Node 2 adjacent to node 1. Node 3 adjacent to 1 and 4. And node 4 is adjacent to node 3. So Elise is at 0, so we'll do a DFS search on 0 first. So we look at 0 adjacent to 1. We come to 1. Make sure we increment the time. So now I know 1. Node 0 is the parent, so we skip that one. Node 2, so we come to node 2. Make sure we increment the time again. Node 1 is the parent of node 2, so we could skip this one. And now that we have finished node 2, we can add 2 to the result for this path. Now, since we have finished node 2, we can backtrace to node 1 since we haven't done node 3 yet. So reset the time back to 1. And then also reset the 0 because now we're on a different path. So in the end, we will see whichever path leads the most to node 1 as we backtrack on the way back, and then we will choose that path. But for now, we'll put it back to 0. So now node 1 needs to look at node 3. We come to node 3. Node 1's the parent, skip this one. Oh, sorry. We need to increment the time first, and then now we come to node 4. So we come to node 4, increment the time to 3. Node 4 has a parent that's 3, so we skip it. Now that we have finished, we'll add 6 to this path that we're on. Trace back on this path. So the time at this node was 2. So since the time is greater than Bob distance, we don't need to add -4. Now we trace back to 1. So the time is 1. But before we do any calculation, since we're tracing back, we need to edit the Bob distance since Bob is going 1 this way. Since 1 is equal to 1, we only add the half credit. So we will add 8. And since it's better to add 2 to 6 and 2 to 2, then we will keep 8 as the net income result. Now we trace back to 0. So edit the time it takes Bob and back to node 0. So time is 0. 0 is less than 2. So we do the full price, subtract 2 to 8. So the result is 6, and that would be what we return. So the time complexity of this example would be O of n, because we will have to look at each node, and n is the number of nodes. And the space complexity will also be O of n because of the recursive stack that we may create. So now let's get to the coding part. So first, we will set up the n variable as the length of amount, and then we'll set up the tree list to empty list initially for I in range self.n, so the length of amount. And then we will have to set up the bob distance array, so self.n times self.n. And then we need to make sure Bob's starting distance is 0, so bob distance of self.bob distance of Bob will have to set to 0. So now we can set up our tree list. So for edge and edges, self.tree of edge 0 append edge 1, and edge 1 will also have to append edge 0 when we iterate through that edges list that we are initially given with at the input. That's how we can add it all to the tree list. And now we can make our recursive call. So we'll call find self.find. So 0 will be the starting node, parent will be the second parameter, so it'll start at -1, and then the second 0 is time, and then bob and amount. So yeah, node, parent, time, bob, and amount. So yeah, we can define our find function. Initially, the income will be 0, and the max path float of -infinity. Initially, it will be full of -infinity. So now we loop through whatever we have in that node. So for adjacent in self.tree of node, any adjacent ones, and if the adjacent node does not equal the parent, then we will execute. If not, we'll skip it. So now we calculate the max path up to that point. It will be either the max of max path, or recursively call it and see if we can find it anywhere else. Node time plus 1, bob amount, and then so now we need to add the bob distance before we do our calculation. So bob distance on node is the minimum of self.bob distance or self.bob distance of adjacency plus 1. So we're adding the time that it takes Bob to get there, or what we have initially. Now after having the bob distance node calculated, then we can start doing our calculation. So if it is greater than time, then we will add the full income or decrease the full price. If it is equal, then we will just do half. So yeah, we will only add half or subtract half. And then in the end, we can return income if the max path is flow of -infinity. Otherwise, we need to add income to whatever we have already added, so the max path. So if max path is -infinity, that means we're still tracing forward and not backtracking yet. Alright, let's see if it works. Okay, perfect. Hope this was helpful. Thank you all for watching. If you have any questions or comments, feel free to leave it down in the comment section below, and I hope to see you all again soon.